Hi guys, we're going to go over a couple practice problems that will help us move forward to titrations tomorrow. So we're going to look at a for practice problem. It's very similar to this example. So if you need to go back and follow the book's step-by-step process where it explains how to find the pH of a buffered solution, here is another example. I'm going to do for practice 17.2, which was also in the Google Jamboard that I shared with you guys a few days ago. So for practice 17.2, says calculate the pH of a buffer solution that is 0.25 molar HCN and 0.170 molar KCN. For HCN, the Ka value is that. The pKa is 9.31. Use both the equilibrium approach and the Henderson-Hasselbalch approach. So let's write out what we have going on here. We have a given amount of 0.250 HCN. We have 0.170 molar, I should have put molar, KCN, which is going to ionize. The K is the conjugate of a strong base, KOH. So the K plus is just going to be floating around in our solution, being a spectator ion, not interacting with water. And also what I'm really worried about is that Cn minus. Okay, now the process of going through and seeing what is the salt going to separate into, what are the conjugate base and the conjugate acid, that is challenging. Okay, so keep working with those. Don't give up. Keep working to see what it's going to separate into. Okay, so this is a buffer. It already told me that, meaning I have an equilibrium between these two things going on. And it also gave me the Ka value of that HCN. The Ka value is 4.9 times 10 to the negative 10. 4.9 times 10 to the negative 10. Okay, so what I'm going to need is, and the question I didn't even write, what is the pH? Okay, what is the pH? So I need to find H plus. H plus is not given anywhere in here. It is going to come off of this HCN in our equilibrium. So it's going to say HCN is in equilibrium with Cn minus plus that H plus that's going to come off, or we could call it H3O plus. Let's just call it H plus to make our lives easier. Okay, you would have to add water to the left side in order to do that. H plus, the values are the same whether you use H3O plus and H plus, so it's up to you which version you want. Okay, and then I'm giving my starting amount. So my HCN, my initial concentration is 0.250. Concentration of Cn minus 0.170. How much is it going to change by, and what is it going to be at equilibrium? That's what we have to find out. This is approximately 0. Okay. And this is going to go down by a certain amount. These are going to go up by a certain amount. Comparing 0.250, our starting concentration of HCN, to this Ka, which is times 10 to the negative 10th power, means a very tiny amount of product is going to form. So if I start with 0.25 molar, it's going to go down by such a small amount that X is going to be small and negligible in this problem. So I'm going to get 0.250 minus X, but then I'm going to make a note in red that X is small. Okay. And so what I get over here is 0.170, and the same thing is going to happen actually. That's plus X, but X is small. And X, whoops, let's make that black. So this 0.17 is going to go up by a tiny amount, but it's going to go up by 0.000000 something. So it's essentially, it would round to 0.17 anyways. Okay, so now I have my Ka, which is going to be these on top, Cn minus. Always write this out because sometimes you get a point just for writing it. Okay, so just write it out to be safe. And HCN goes on the bottom. If you had H2O, it would not be included here because it's a pure liquid. And I can plug in my values now. So I have Cn minus, that's 0.170 molar, times H plus, which is X, over 0.250 molar. So the molarity is going to cancel. And that is equal to the value of Ka, which is 4.9 times 10 to the negative 10th. So I'm going to solve for x by multiplying both sides by 0.25. So that cancels. 0.25, it's getting a little crowded. Okay, and then divide by that 0.17. And then we get my calculator, and let's do that. Okay, so I have 4.9 exponent negative 10. Okay, that looks good, times 0.25 equals, and then I would have to divide by the 0.17 to solve it. Divided by 0.7 equals 7.206. 7.206 times 10 to the negative 10. Double check that exponent. Yes. Okay. So that is my x, which is equal to, always define this guy, the H plus concentration. And since that's the hydrogen concentration, to get the pH, it's the negative log of that H plus concentration, which is the negative log of this guy. So I would hit log negative 9.14. I had 3 sig figs, so I want 3 decimal places. 9.142. Okay, so that is a lot of work, I know. We have to do an ice chart. We have to find our x, which is, in this case, the hydrogen concentration, take the negative log, all of that. There is another way, okay, and this is the second part of this problem. It says use the Henderson, I'm going to spell it wrong, Henderson-Hasselbalch. Let's check it out. S-double-S-B-A-L-C-H. B-A-L-C-H. Equation is just like a little cheat in order to find the pH of a buffer. Okay, pH of a buffer. Okay, your book goes through how to calculate or find the Henderson-Hasselbalch equation. It is right here. You can read through, it makes a lot of sense of how they find this. It's not given on the list of equations, so you would have to memorize it. It's not super hard to memorize. It's not a crazy complicated equation. But the pH of a buffer is equal to the pKa plus the log of the base over the acid. So pH equals pKa plus the log of the base over the acid, because the base is my, the conjugate base is my product. It goes on top, the acid goes on the bottom. Okay, and that actually makes this question really easy. pH is going to be, they gave us the pKa in the question down here. pKa was 9 point something. pKa 9.31. So it's 9.31 plus the log of my base, that's the Cn minus, so 0.17, over the acid, 0.250. Okay, and let's see what we get. So I'm going to take clear, 0.17 divided by 0.25 equals, take the log of that. Okay, now I want you to see something really important. The log of 0.68 is negative 0.167. Anytime you have a decimal and you're taking the log of a decimal, is you're going to get a negative value. Why is that? Because remember that log, you're saying 10 to what exponent would give me this number. So if you're taking, for example, I'll do an easy one, 0.1. Okay, the log of that, 10 to what exponent would give you 0.1? It's going to be 10 to the negative 1. So the log of that decimal will be a negative value because it's going to be 10 to some negative exponent there. Okay, so I had 0.68 right here. When I take the log of that, I get negative 0.16. I'm going to add that to my pKa plus 9.31 equals 9.143. 9.143. So the pKa was 9.3, pH is 9.143. Let's compare it to the one that took us a lot longer because we had to do the ice chart, 9.143 to 9.142. So they are so close that doing this way makes a lot of sense. There is a note in your book that the Henderson-Hasselbalch equation only works if, hopefully you guessed it, x is small. So this is assuming, this equation assumes that x is small from the get-go. Okay, and the other one, you could actually check whether x is small works. In the Henderson-Hasselbalch, you can't check that. Okay, it just tells you the pH assuming that x is small, which it almost always is on the AP test. So that's just a heads up. Okay, all right. So that was for practice 17.2, finding the pH of a buffer. I did, and Henderson-Hasselbalch, I did want to look at this conceptual connection. A buffer contains the weak acid HA, its conjugate base A-. The weak acid has a pKa of 4.82. The buffer has a pH of 4.25. The pH is less than the pKa, just like our last example. So that log of base over acid is going to be a negative value. Which statement is true of the relative concentration of weak acid and conjugate base in the buffer? So, in other words, for this conceptual connection, I have my log of my base over acid, and this is a negative value, which means that it is going to be a decimal. Okay, the fraction is going to be a decimal. So that means, therefore, the acid is going to be greater than the base. Okay, and let's find that. Which one has the acid greater than the base? That would be A. What if they were equal? If these two were equal, I would get 1. 10 to what exponent is 1? 0. So that's another really important point for this Henderson-Hasselbalch equation. When base equals acid, that means that this guy would essentially cancel out to 0. So pH and pKa would be the same value. So a buffer with perfectly balanced amounts of acid and base, the pH is equal to the pKa. Okay, that's going to be really useful down the road as well. Okay. So calculating changes in a buffered solution. I'm going to save that for the next video. You have actually 2 parts to these calculations. These aren't very often seen on the AP test. Okay, I'm going to skip it for now. I will make a video going over one of those examples, however. And what I wanted to very quickly talk about is way down here, buffer effectiveness and buffer range. So I wanted to get to 17.3. For our buffer to be effective and the range of that buffer, what you want. I don't think this does a very good job of summarizing it. In this section, we examine two factors, the relative amount of the acid in conjugate base and the absolute concentration of the acid in the base. Okay, so what we want right here, let's summarize this. A buffer is most effective, most resistant to pH change when the concentration of acid and base are high. So we want for a quote unquote good buffer, which means it resists the change to pH a lot, we need, number one, high concentrations of acid and conjugate base. Okay, so we want higher amounts. So for example, 1 molar is better for resisting pH change than, say, 0.01 molar. Okay, the higher the concentration, the better. 2, chapter 17.3 in a very small nutshell. Second thing is, so that's the absolute concentration. So we want them to be high. And actually your book goes through and calculates a 0.5 and 0.5 compared to a 0.05 and 0.05. And it tells how much the pH changes. So this one only changes by 0.4%. This one changes by 3.6%. Okay, so the one with higher concentration is more effective. Did I skip over? I did. I'm sorry. These are in the reverse order, but that's okay. The buffer is most effective, most resistant when the concentrations are equal. That's the second point. For a good buffer, concentrations of acid equals concentration of acid equals concentration of base. So you saw in the example it did 0.5 to 0.5 or 0.05, 0.05. You want the amounts to be equal. The more imbalanced the acid and base are, the less effective the buffer will be. Okay. All right, so that is what I wanted to go over for this section. There's a lot of examples you can look at, but if you just remember those 2 points, you should be good for the effectiveness of a buffer. The range is how much you can add before the buffer is ruined. So you can add too much acid to a buffer and you've used up all of the conjugate base in that equilibrium. And so then any extra acid you add, it's just going to initially just dramatically change the pH. Okay, and it summarizes it right here for us really well. The effective range for a buffering system is 1 pH unit on either side of the pKa. So when we were looking at the buffer with a pH of 9.31, the range would be between 9.31 would be 8.31 to 10.31. Okay, so 1 pH unit on either side of that pKa. That, I believe, is it. This is kind of interesting about the buffer in our blood, buffer capacity, and we will get to titrations. Have a great day.